So in this video, we will learn about the concept of stereochemistry and how to apply stereochemical configurations to molecules. So to take a step back, the reason we care about stereochemistry is because a chemical formula can refer to many different structures. Right? So we already saw that there was this problem of being given a formula and being able to come up with multiple different valid Lewis structures. Another way to refer to the relationship between those structures you could come up with are to call them isomers, and specifically those are structural isomers. So examples of that would be, let's say I gave you C6H9NO here. These are two valid structures you could come up for that chemical formula. The way I think about it is that there is different connectivity between atoms in these two isomers. And more specifically, the sigma bonds are different. It's almost like you had to break bonds between atoms here and reconnect things to be able to get here. Another sort of relationship between drawings or structures is the idea of resonance forms. I'm going to put that at the bottom here. So resonance forms, if you look at them, they have the exact same sigma bond connectivity between the atoms, but there are changes in how pairs of electrons are either in the pi bonds or are lone pairs. So an example of that would be this pair of resonance forms for a single molecule here. So again, the sigma bonds connecting the 6 carbon atoms have not changed at all, but some of the pi bonds have changed. And so I put the resonance forms at the bottom because there's essentially no change, right? We don't have two different molecules here. We have two different drawings. We have two different resonance forms. So between structural isomers and resonance forms, where I would think of structural isomers as being pretty different from each other and resonance forms as being the exact same molecule, there are what are called stereoisomers. And so stereoisomers have the same connectivity between atoms, but at the same time, these structures are not identical. What I mean by that is that if I look up here, I said that I had to break kind of nitrogen here is attached to this carbon, but the nitrogen here is attached to 2 carbons instead of 3. And so you have to kind of separate certain atoms from each other to get from one structure to the other. Right? The connectivity is different. When you're dealing with stereoisomers, that atom that you're thinking about is always going to be attached to the same other atoms, but maybe in a different orientation. So it'll help to look at an example here. So I have two molecules, and if you're looking at them, this is a bromo-chloro-fluoroiodomethane, and so is this. This is bromo-chloro-fluoroiodomethane. Right? So they would have the same IUPAC name if we were just going by that alphabetical listing of the prefixes in the molecule. But at the same time, if you look at these are not identical, right? So I'll bring out some models of these molecules so we can see what's going on. And so the molecule on the left here is going to match the one that I drew, and then the one on the right here matches what I drew here. So I tried to color code the atoms so it'd be a little bit easier to follow. And the way you kind of test if structures are identical is to try to overlap them in your mind. Right? So if I were to do that with these models, I would go like this. And what you'll see is that you can get these two atoms, the blue and the black atoms here, to kind of be the same. But you'll never get all 4 of the groups attached to the middle carbon to be identical. No matter how you kind of rotate these around, you'll never be able to do that. So these two are different molecules, and we call these stereoisomers of each other. This pair of molecules are stereoisomers. Going back to the connectivity idea, we can look at this central atom, this carbon here. No matter what, it's always attached to the black iodine, same in left and right. Always attached to the red fluorine, it's the same on the left and right. You're attached to the gray chlorine, same in the left and right. Finally, always attached to a bromine, same thing in both, right? So the connectivity is the same, but the orientation of that connectivity is different here. There is a little bit of terminology that's worth going over when it comes to stereochemistry. So a first idea is that objects and molecules are going to be either chiral or achiral. And so the definition of these terms chiral and achiral are as follows. A chiral object does not have an internal mirror plane, while an achiral object has an internal mirror plane. So I think it's helpful to look at some examples. So if I take this stick figure, This is an achiral object, because if I go through, I can either go like this and bisect this drawing and look at it from left to right, and see that the left side is a mirror image of the right side, or I could actually bisect this drawing in the plane of the drawing like so, and kind of cut the stick figure into a top half above the page and a bottom half below the page, and those two halves would be mirror images of each other. Right? So there's multiple planes of symmetry internal in this object that make it thus achiral. For actual humans, however, our internal organs are not symmetric on either side of our halves, and so because of that, the actual human, or my crude stick figure drawing here, would be considered chiral. In the world of molecules, you can look at our tetrahalogenated methane from the previous slide, and if you look at this, there's no way to draw a mirror plane that divides this molecule into identical halves. So this molecule right here would be chiral. Now this cyclopropane molecule right here is an achiral molecule, because I can think of a plane being kind of in this page, right? In the plane of the drawing. Right? And that's important to remember, because I did draw wedges and hashes, but that doesn't automatically make something chiral or not chiral. Right? You have to take into account relative orientations and the identity of the atoms in the molecule. And so if you're trying to visualize this, what we're trying to see is that this plane kind of puts the hash group behind it and the wedge group in front, and so we're kind of cutting that molecule in half, so the top half is the same as the bottom half. Another way to think of chirality, or whether or not an object is chiral, is to actually look at the mirror image of the entire object or molecule. So for example, if I take my tetrahalogenated methane again, and I go through, I can draw the exact mirror image of it. So then what I'm doing is kind of reflecting across. So the bromine is closest to the mirror here, so I'm going to put it closer here. Iodine is a little further away, put it here. That's a hash bromine, wedge bromine, so on and so forth. And so that's just another way to check. Either the internal plane method or the comparison of mirror images will check. And so if I take my mirror image, these are not the same. There's no way to get these the same. It'll be a lot easier to do this with a model, much easier to visualize, but eventually this will be something we want to be able to do kind of in our minds. So you might have noticed that this carbon atom in the middle seems to kind of be the source of the chirality in the molecule. So that turns out to be true, and what we see in organic molecules is that atoms that are tetrahedral, so it doesn't have to be a carbon, just any atom that's tetrahedral and is attached to 4 different groups around it, can be kind of a source of chirality, and those are called stereocenters. It also turns out that if you take stereoisomers, we can kind of sub-classify stereoisomers, and there are 2 different versions of stereoisomers. So if the stereoisomers you're considering are mirror images of each other, then they are called enantiomers. If the 2 stereoisomers you're looking at are not mirror images of each other, then they are called diastereomers. So let's go through some examples of determining whether things are enantiomers or diastereomers. So the first one is our tetrahalogenated methane. We've already seen that these 2 drawings are mirror images of each other. And so in other words, the mirror image of the left molecule here is the same thing as the right molecule or right drawing. Therefore, these are enantiomers. Now let's look at this pair of alkenes. Here, no matter what I do, if I try to draw the mirror image of that molecule, I would get to drawing like this one, and what I find is that this mirror image of the molecule here is never the same as the drawing on the right. So these are not mirror images of each other. Therefore, this pair of blue molecules are diastereomers. Here's one more pair of stereoisomers, and you can kind of go through the same process and figure out that these are diastereomers of each other. One final thing I want to mention is that it's kind of an interesting situation, because the molecule on the right actually has an internal mirror plane, And so it's an achiral molecule even though it has stereocenters in it. And when that happens, so when you have a molecule that is achiral but has stereocenters, we call that a meso compound. So with those terms out of the way, it's important for us to think about how can we refer to stereoisomers in a way that distinguishes them from each other. In other words, how do we assign an IUPAC name that informs us which stereoisomer of a given molecule we're actually talking about? And so the way we do that is we give what are called stereochemical configurations, and those are attached to the names of the molecules. So just to give you an example, here I am showing you a pair of enantiomers. So these two molecules are enantiomers of each other. The top one would be called R2-bromobutane, and the bottom one turns out to be the S2-bromobutane. And so that means that if you see the R here in the 2-bromobutane, you should be able to draw this specific drawing. If you see an S here, that would tell you to draw this specific drawing. We'll get to how to do that in a minute. When it comes to alkenes, those are not referred to using R and S because alkenes don't have stereocenters in them, so R and S are specific for stereocenters. When we have alkenes, what we use is called either an E or a Z system. The way you determine whether something is R or S or if it's E or Z is by evaluating the relative importance of groups attached. So for R and S, we'd be looking at the groups attached to the stereocenter. For E and Z, we're looking at the groups attached to the double bond here. These rankings are determined using what are called the Kahn-Ingold-Prelog rules or just CIP rules. So I want to just go through how we figure out E and Z or R and S before we actually talk about the rankings, because the rankings take a little bit more time. So we'll start with stereocenters. So if I have a molecule that has a stereocenter in it, so a tetrahedral atom with 4 different groups around it, and let's say I've determined that the rankings go like this. So 1, 4, 2, 3. Right? So I'm going to call 1 the highest ranking and 4 the lowest ranking. The way that we assign R or S is we go and look at the central atom. So I want to put my eye in a perspective where I'm looking at the tetrahedral atom or the stereocenter, and I want to put the lowest ranked group behind that tetrahedral atom. And so what that looks like is something like this, where my 1 is there. So the group 4 is not visible because it's hidden behind that tetrahedral atom. And on the left here, I would have 3 and 2 like this. And after I've done that, then I go through and determine whether the rankings go in clockwise or counterclockwise order. So here I see that we go from 1 to 2, 2 to 3, like this. That's clockwise. And so clockwise tells us that that tetrahedral atom is an R configuration. All right, let's look at another example. So let's say I give you a stereocenter with rankings that look like this here. Right. So I still want to do the same thing. I want to look at the stereocenter, and I want to place the lowest priority group behind the stereocenter. That means I'm looking at this bond right here, and that means that when I look at it, I need to take this perspective. So I need to put my eyeball here and look that way. If I do that, then what I'll see is I can put the highest ranked group at the top here, and if I do that, what I'm really doing is I'm kind of altering my drawing here a little bit to take the perspective of being like this. Right, so I'm putting the group 1 and 4 in the same plane, so that helps me visualize where 2 and 3 go. And when I do that, then I should see that 2 would be to the left, 3 would be to the right. Then I go through and see what direction I'm going with these groups. Then I see that we're going counterclockwise, and if it's counterclockwise, we call that an S configuration. For E and Z, the idea is similar, so I'm going to take a alkene here. What we do, however, is we actually compare the two halves of the alkene separately. So there are two separate problems of rankings. And so what we're doing is actually we're asking, on the carbon on the left here, which one is higher? On the carbon on the right here, which one is higher? Well, so in this situation, it looks like I have both of the lower carbons as the higher ranked group. And so if that happens, what we're kind of viewing is that then I take the molecule like this and see that they're on the same side of the red line. So that would be called a cis or same alkene, same-sided alkene, so the higher ranked groups are on the same side. Or in the EZ nomenclature, we would call that Z. I'll show you what that looks like for the other possibility. So let's say my two highest ranked groups go kind of across the double bond is what I would say. Then what we have is called a trans alkene, or it's called an E-alkene in IUPAC nomenclature. All right, that's great. So if you knew the rankings, it would be possible to go through and assign RS or EZ to a given molecule. So how do we determine the rankings? Let's go back to the CIP rules. The CIP rules follow a pretty logical system. So we rank groups by atomic weight. So we really look at atoms, not the entire group, but just rather one atom at a time. And the heavier that atom is, the higher rank it is. So for example, we can look at two situations here. The molecule on the left, I would start at my stereocenter, so I can give that a little star telling me that's my stereocenter. Then I would go through and rank these from heaviest to lightest. So this carbon is attached to an iodine, that should be the heaviest. Bromine should be the second one, chlorine is the third one, fluorine is the fourth one. On the alkene to the right here, I have two carbons we have to look at. So these are not stereocenters, but just two carbons we have to look at. Looks like the left carbon is attached to a heavier isotope of oxygen and a lower or lighter isotope of oxygen. So we should rank these as 1 and 2. On the right here, we would rank fluorine as... On the right here, we should rank chlorine as the 1 and then fluorine as the 2. So sometimes you'll do this ranking and you'll find that, well, actually I have two atoms, let's say, that are identical, right? I can't judge which one is heavier. And if that's the case, then you keep going further down the chain as much as you can, one atom at a time. So, for example, here, if I were looking at this, I would look at this carbon. I would remember that there is a hydrogen in the back that I haven't drawn. If I'm looking at this, I think I should be able to identify that bromine is the heaviest, so the highest ranked, and hydrogen is the lightest, so that's the lowest ranked. However, I have now two carbons, right? So I don't know, just looking at those atoms, which one is the more highly ranked one. So what we're supposed to do is to then go down the chain. And so I think it's helpful to draw this out. So I'm going to start at my carbon that was the central stereocenter, and then I'm going to go outwards. So on the right, it looks like I have a carbon. On the left, I also have a carbon. This left carbon is attached to 3 hydrogens, and the right carbon is attached to 2 hydrogens and a carbon. So again, I was starting from here. I got to a first level of looking at kind of here and decided those were the same. So then I had to go to the next level, kind of looking at those 3 atoms, right? So it's almost like I'm treating this as another stereocenter kind of a problem. And what I find is that the right carbon has the heavier atom attached to it. So this is kind of a CHH. Here it's HHH. That means this overall right side is the higher ranked group. So I can go back and give this the 2, and by consequence then go back and give this group the 3. And so an important thing to realize here is that, again, we're going one atom at a time. So I can put the heaviest possible atom way further down the chain here, but that heavy atom out here makes no difference if there is a earlier point of difference in the molecule. The third thing that shows up when we're dealing with assigning R or S, or rankings and priorities, is that there are pi bonds in molecules, and there's often pi bonds in molecules. So the way this is handled is Because our goal is to always kind of build a tree like this, where we're dealing with single bonds outwards, when we run into a pi bond, we essentially break that pi bond in half to make what's called a phantom bond and a phantom atom. And I think it's helpful to look at this through examples. So this molecule has a stereocenter. Looks like that stereocenter is attached to a hydrogen in the back, so I can give that the 4. But then it's attached to 3 carbons, so that means I need to go through and draw out kind of my stereochemical tree here. So I'll start at that central carbon, that a little star. I'm going to just ignore the hydrogen because I already know that I've taken care of its ranking. So if I'm looking at the carbon right here, this carbon is then attached to a hydrogen, another carbon, and another carbon. The upper left carbon right here is double bonded to an oxygen, so we need to create a phantom bond situation. So what I do is I first draw an oxygen, so that kind of accounts for the real oxygen. And my phantom bond is I take that pi bond and split it off this way. And then I create a phantom atom, which I will put in parentheses to indicate that it's not a real atom that actually exists in the molecule. So again, this part is supposed to be referring to the double bond here. Additionally, we have to create the other half of the double bond, so then the oxygen is attached to a phantom carbon. So you can view this bond plus this bond as being the missing double bond right here. Finally, that carbon's also attached to a hydrogen that we can't forget. And then at the bottom here, it looks like this carbon, this one, attached to 2 oxygens and a hydrogen. So 2 oxygens, hydrogen. Based off of this now, I know that this side is not as highly ranked because I have a carbon attached to carbon, hydrogen, hydrogen, whereas on these 2 groups I have a carbon attached to oxygens. So I can go back to my actual molecule, give the group here a 3. When I go to my oxygen-containing groups, what I find is that I essentially have this carbon is what I would call oxygen, oxygen, hydrogen attached. This carbon is what I would call oxygen, phantom oxygen, hydrogen attached. This phantom oxygen is not as highly ranked because it's not real. That means I choose the group at the bottom here as the more highly ranked group. Overall, that helps me decide that the group down here is 1. The aldehyde is actually the 2. Then, overall, that is going to tell me that this molecule should be the R configuration. So the point of this video was to talk about situations where, given a chemical formula, we have what seem to be very similar molecules that have the same sigma bond connectivity, but in the end are not identical. This is really important because in chemical reactions, it is often the case that a reaction can produce multiple different stereoisomers